Right, so welcome everyone. This is a great pleasure to have you. And here we are going to talk about things, mathematics or physics on the board. So today what I'm going to talk about has to do with a follow-up from a previous video where we tried to describe the electromagnetic field in terms of the exterior calculus. And I said that I wanted then to go further and to look at why actually this is a powerful way of representing electromagnetism in general. In this short video today, the goal is to see how gauge, so-called gauge invariance, actually comes about very, very easily, essentially in two lines at best. Or at best, no, actually at most. So that's what we are going to do today. Right, so let's start first by summarizing a bit what we've done last time. So provided you've looked at the video where this is related to calculus or exterior calculus, essentially you start from a so-called potential one form. So potential one form here is going to be expressed as A is equal to minus V dt plus AX dx plus AY dy plus AZ dz. So that's the so-called potential differential one form, okay, or exterior one form. And then what we introduce is the exterior derivative, and then I apply this exterior derivative onto A, and I call the outcome of that the electromagnetic field 2 form. And essentially the 2 form I'm going to obtain, I can interpret it, so please go see the video corresponding to it, as let's say an electric field. Here I'm just referring to this as a sort of one form relative to the spatial differential components, and then there is basically a 2 form magnetic field here. Okay, so that's essentially where we left last time. Now, a very, very interesting feature is that A is basically a field, a one form. So the thing is that I can say that I can imagine, okay, I can imagine basically to supplement an existing A by simply adding to it the exterior derivative D of a 0 form. So imagine then some A prime, so that's another potential one form that is going to be equal to A and then plus D, for example, F, like so, and here F is a 0 form. Okay, so that's kind of the idea. A 0 form, by the way, is simply a scalar function, f of x, y, and z, for example, and t. Okay, so so that's it. Now, when I actually look at what would be then the corresponding f prime, that's equal to the exterior derivative applied to a prime, then this is going to be equal to dA, and then plus the exterior derivative applied twice onto f. Okay. But as it turns out, that's a theorem of exterior calculus, d squared f, so applying twice the applying twice, sorry, the exterior derivative on any basically k form. It doesn't matter whether it's a 0, 1, 2, or 3, or whatever form, is going to return exactly 0. Okay, so this is actually equal to 0 by the definition of the exterior derivative. And so, therefore, it follows that this is equal to dA, and so this is equal to f. So what it means is that f prime or f are invariant under any basically addition of df into the one form potential. Okay, and so what that means, therefore, is that we have that f is invariant or independent, but invariant, and any transformation of A of the form that we've seen above. Okay, of the form and that's A prime is equal to A plus df. And in principle, that's for any function f that is kind of differentiable, essentially. Okay, so that's kind of the idea. Let's see very quickly how we can retrieve the traditional kind of gauge transformations. That's where you kind of need to do things a bit more properly within the definitions of the electric and magnetic field. But here you see that gauge invariance. So that's called gauge invariance. So let's name this thing. So that's called gauge invariance. And then let's substitute then this particular thing. So if I actually say that I've got A prime is equal therefore to minus V dt plus AX plus AY dy plus AZ dz, and then I simply put df. So df is going to be df dt dt plus df dx dx plus df dy dy, and then plus df dz dz. Okay, so we can simply look at this. Then essentially what I can say is that this is minus, and then here I'm going to get v minus df dt, okay, and then times dt, and then here I'm going to get plus ax, and so here ax is going to be plus df dx, and then that's actually dx plus ay plus df dy, and then dy, and then plus az plus df dz, and then that's dz. Okay, and so what we do in the end is essentially that we call these things v prime, and then here this is going to be ax prime, and here ay prime, and here az prime. Okay, so the bottom line is that here we recognize the traditional transformations that have to be occurring on A and under which the electromagnetic field is actually invariant. And so this from there we can have the vector form, like the more conventional vector form of this transformation. You've got that A prime is going to be equal to A plus the gradient of some function, and then v prime is therefore equal to v minus then df over dt. Okay, so if you apply these particular transformations, then the electromagnetic field is actually invariant under those. Okay, so again, actually this is compactly written in basically 2 lines, and here I've just written this in order for you to essentially latch onto things you may have seen already in any kind of electrodynamics or electromagnetism courses, but basically, like, the whole physics is there. Okay, the whole math and physics, if you will, is already there. Okay, so that's it for today's video, and basically if you have any comments or questions, please do let them in the comment section, and otherwise see you in the next video.